Hey everybody, Barav Zes. Thanks for having me here, all the way from California. I'm a PhD student in artificial intelligence at UC Berkeley, and today I'm going to give a tour of deep learning for vision, highlight some of what's possible, and then give a bit of advice on how you could do it yourself. One thing we can see already in this example is that our framework, Caffe, knows what coffee is. Now, if you decide to join in and do this kind of work too, you might also teach the machine how to recognize search. So let's begin and see what kind of work we can do in this area. So to begin, I'm just going to give a brief overview of why deep learning at all. There's many kinds of machine learning out there, and there are many approaches to vision. But deep learning will give us certain abilities that have really changed things over the last 5 to 10 years. And having done that, I'll also introduce various steps and things you could do on your own because of open source frameworks and open source science. So to begin, why should we do deep learning at all? And the answer is that it lets us do end-to-end learning for many kinds of tasks, where end-to-end means that we go all the way from the input to the problem, such as a single image, to the output, like knowing what's in it. And we do that through a learning system so that if we change the data, if we instead of collecting images of dogs, collect, say, images of politicians, we can do that new problem without having to start again from scratch. So I'm going to focus on vision, because that's the subject of my own research. But likewise, there's a lot done in speech. Deep learning powers the kind of voice recognition that's used in your mobile phones or smart home appliances. Also in text, things like machine translation. And finally, even in automation and control in robotics. People are beginning to use deep learning to do some more advanced factory work, although that's still in the very early stages. So today, we're going to look at vision. And I'll begin by introducing some visual recognition tasks. One of the most fundamental is classification. So we have an image that comes in, and we want to know either what kind of image it is, like if it's outside or inside, and what the contents of the image are. So in this case, we'd want to know that there are cars, a horse, and a person. And this is challenging because there's just so much variety in the world, right? We're very good at this as humans, but machines have to learn this from nothing. And the lighting can be different. People can take different poses with their bodies. There might be lots of other things in the scene. Or we might want to know very specific things, like not just that there's a horse here, but like the exact species of horse. Now let's see what deep learning has done for this problem. Here on this graph, we're looking at the error rate, so lower is better, on a standard visual benchmark called ImageNet. And what we can see, first of all, is that the error has gone down dramatically. It's 10% of what it was. It started near 30 and is now only about 3. And what's also shown here is the depth of the network, which I'll get into in more detail later. But basically, as our models have grown, going from very shallow, just a single layer, to over 100 layers, we've also reduced the error. And this has happened very quickly. This has only been in the span of 5 years. And results are even better now in 2018. And what I'll point out is that these models that are highlighted in red were either reproduced in Caffe, which is the open source framework that we make at Berkeley. Those are the dotted lines, or originally made in Caffe. So this is a tool that's used not by us, but actually by universities and companies around the world. And the same is true for the next generation of frameworks. So now that we've seen classification, I want to move on to a more advanced problem, which is detection, where you want to know not just what's in an image, but exactly where the objects are, as you can see in these boxes around the person and the horse and so forth. So we need to both know what and where. And this can be difficult because we want to get every instance. Like I'd want to know where every one of you are in the audience, and not just know people, because people's not that useful an output if I wanted to, say, interact with each of you. We see the same kind of trend in detection. Before deep learning, on the left side, there was improvement for some years, but then you see between 2011 and 2012, there was a complete stall, and no progress was made. And then on switching to deep learning, on the right side, progress was even steeper than before, and now actually somewhat works. We'll see some outputs later that are very impressive. And so methods to do this are state-of-the-art, and they're in Caffe, and also its successor, Caffe 2. And there are open source implementations that you can use yourself. Having looked at detection, let's look now at an even more spatially precise task which is semantic segmentation, where we want to know what every pixel is. It's not even enough to just put a box around it. You would want my exact outline. And so here, there's a tension between knowing what something is, which requires you look at a very large global scope to know what it is. If you only saw just a pixel of my face, you might not know it's even a face, much less me in particular. And also the amount of computation, because there are many pixels in an image, and we want to process all of them. So as you might have guessed in this progression, this is also done by deep learning nowadays. If we look at just a few years of a standard global contest, deep learning methods in Caffe improved the results more than 50% relative in the span of only a year, while also getting 100 times faster, which makes them actually practical, and in some cases even able to run real time in video. And many of these methods are now part of what powers current methods for autonomous driving, and also dealing with large amounts of data from, say, satellites, where before we simply didn't have methods fast enough to do these problems. These are likewise in Caffe, Caffe 2, and PyTorch, among other frameworks. And there are reference implementations that you can try yourself. So having looked at some of this research, you still might wonder, does any of this actually matter? Like, can I do this myself? Can it be useful? Could I use it in a business? And I like to illustrate it with this comic from XKCD, where someone has an idea. They want users to be able to take photos and check if it's a national park. And that's very simple. They just look up the coordinates, right? That's a very simple computer science problem. Are the coordinates in this box? But they also want to know if it's a bird. And suddenly they say, oh, I need a research team, 5 years, a bunch of money. How can we do this? And these things seem kind of similar, right? Where is something? What is something? But what, historically, has been so much harder. And yet, Flickr did this as a weekend project, just for fun, part of their developer team. And they were able to do this because of this change in vision that's been brought by deep learning. And the way they did it was just a day's work of Caffe by taking a model where I can't go into the exact structure in this talk, but basically it has a bunch of reusable parts so that you can assemble your own and take an existing model and change it and improve it. And that's what they did. They took open models that are shared for free in Caffe and then kept training them to identify many species of birds, even though that wasn't the original purpose of it. And this kind of transfer and reuse is part of what makes deep learning so powerful and so useful for so many problems. And so I'm going to go over some things that have been done in Caffe, but this kind of work can now be done in many other frameworks too. So you would ask, what exactly is Caffe, right? Like, what are we doing with all our time spending on it? And it's one part open framework, meaning it's a library of code, but it's also models. We've taken exact models for different tasks. We've already made them, we've trained them, we've documented them, so you can use them too. And it's not just you can use them for what we made them for, because you might not care about recognizing, say, different kinds of cars, but you can keep training these models to do tasks that are more relevant for you. And that's only possible because we've shared the code and all the learned models together, along with examples for many of these tasks that I've been highlighting, like detection or segmentation or classification. So at this point, it's getting a bit older. It's nearly 5 years old. It's been used many times in research with thousands of citations. It has contributors from all over the world, over 250 actually, and has many subscribers on GitHub, as well as forks, so people have their own versions. And at the peak of development, we had more than one change to it a day that was either submitted by the community or made by ourselves in Berkeley. And while the focus has been on vision, it can also do many other tasks, like modeling sequences or doing reinforcement learning, which is not just predicting, but also taking actions, such as for driving cars, or in speech and text, like in translation. And so what it actually is concretely is it's a C++ and CUDA library. Those are common languages for deep learning frameworks now. It has interface command line and Python and MATLAB, Python being the most popular since it's also free and open source. And it's both fast and well tested. This isn't just some research code thrown together by students. It's actually used by companies around the world too. And finally, it lets you go from different phases of your project, just prototyping it on one machine to training it on modern GPUs, then finally deploying it on clusters, all with the same code, which is a pattern that's been followed by further frameworks. So just to give a snapshot of development, this is just a month in the life of Caffe while we were preparing to make its 1.0 release. And you can see it was quite busy. Pull request is a submitted change to the project. We had 22 of them merged in 30 days, and 23 more of them added. So there's even more work to do, with almost 100 issues of discussion all throughout the community. Today, it's more in maintenance. It's a bit quieter, as you can see here, but it's still being developed. So if you're interested, you can work on this yourself or join the efforts on other frameworks too. Because one point is that these are all open source. So finally, I made this point earlier about Caffe not only being code, but it also offers reference models. This means that you get the model definition, so it might be hard to maybe interpret a paper, especially if you're not a researcher, but here we've exactly defined how the model works. So you can use it yourself as defined in code. But we also give all the settings and all the little tricks that make the model actually work. Because even if you have the right definition, if you don't have the right settings to train it on your data, you won't get a good result. So you need all these details, and Caffe packages up all of this. And finally, so that the first step isn't to, buy a GPU server and run something for a month, we just give you the model. You can start right at the last page of the paper, or right at a demo, and then alter it yourself and keep doing it. So the BVLC models, the ones from Berkeley, are all free to use for any purpose. So whether you want to do it as just a fun project, in a startup, or start writing a paper, you can use them for all these reasons. And our community shares models in what we call our model zoo, that has dozens of models for many purposes. Some for biology, like studying slides, others for, say, product search, like find me that lamp, I'd like to buy it, and many other things. You may have heard of these now because model zoos are actually standard across frameworks, but Caffe had the first to actually share pre-trained models. And this opens up both research, but obviously applications too. Because for the first time, many researchers and industrial developers are using the same tools, at least in machine learning and deep learning. And we'll talk more about this at a panel later today at Barcamp. So I'd like to just hint at the model format, which is one that uses a standard serialization library. It's called protobuf. It was actually developed at Google. And what it does is it lets you auto-generate code. So you don't have to write all your own functions of let me load and save the model and do these things. Instead, you define a schema, which is shown at the left. It's just a small excerpt of a very large file that defines all possible Caffe models. But one point is that it then generates code so you can write your models as text and share them more easily. And for instance, further update them. Now, we use this model format in our zoo by combining it with GitHub, which is, of course, a very unofficial solution, but one that's been very practical because everyone can do it for themselves. And the way this works is that you take the format that I just showed on the last slide. You also package up a URL to the learned model so people can download it. And finally, give a checksum just so people know that they've downloaded it correctly. And in this way, people have shared dozens of their own models. So now that I've talked a bit about the framework and just given a quick gist of some of the tasks in Vision, some of you might actually be new to deep learning in general, so I'd like to just give a quick survey of what it actually is and what kinds of models I'm talking about. So to really break it down into its essence, deep learning has two parts. There's just stacking layers, and it's learning them end to end, learning the entire model. And so what does it mean to stack layers? A layer is really just a transformation. We have some data x, we're going to feed it to our layer, and out will come a transformation of it, x prime. And so deep networks are layered models that simply stack many layers of different kinds of transformations. And the way it works is that our network, which is defined as a sequence of all these layers, they run step by step. And so the input to the first becomes the input to the next. And we go step by step throughout until we get to the output. And this is what I meant about end to end, in that our network will solve the whole problem. Now, to learn it, we'll have some error, because we'll have our output, and we'll have a known truth, what we'd like the network to do. And at the end, it's easy to compare these and know if it got it right or wrong. If it got it wrong, we can then pass that error back into the network. And so step by step, it'll make a correction and improve itself. So as a contrast, we can look at shallow learning as opposed to deep learning, where here we're actually going to engineer the solution to our problem. We'll take some data and maybe inspired by engineering or physics or various things, we'll make specific features ourselves and then put them into a learning method. But it can't learn those features. It can only do as well as the features that we design. And there are many in the history of vision. People have worked on this, very intelligent people have worked on this for decades. But now, all of these features, designed with different inspirations, are surpassed by learned representations. And more importantly than them just working better, the new representations and networks can transfer across problems. It used to be if you designed a vision system, say for analyzing MRI of the brain, it would then be useless for doing something with like X-ray scans of bones. They're just too different. But in deep learning, we can actually combine these kinds of data and do even better than using one alone. So again, just to kind of recap it in sum, in deep learning, we'll have our data go in and learn the whole problem, all the way to the output. And so in this sense, it's really the data that decides our model, rather than us, because really it's truly the data that defines the task. And so part of what this is doing is it's letting us cope with the fact that the visual world is just very vast and varied. We can't really describe it by hand. Even if you had to tell someone exactly what your face looked like without actually letting them see you, how would you go about doing it? Right? It's very hard to describe and capture these kinds of things. With deep learning, what we're able to do is actually have it learn hierarchically. So going from very local appearance, just edges, to parts and textures, like eyes and noses, and finally whole faces. And it does this on its own. And likewise, it can capture very varied tasks, like even defining a chair. Such a common object is quite difficult if you think about how many varieties there are. But if we can collect a lot of examples, we can learn this. So I'd like to just give a brief tour of some applications now, so you can see more practically what people are actually doing. And one is that there's an actual demo online you can try for yourself. If you go to this site, you can either use an example we have built in to quickly see, internet's going a little slow, to see that this is a cat here. If it loads, there we go. I guess a lot of people might be on Wi-Fi. Or we can try an image from Armenia and see what Caffe thinks of it. And you're welcome to try this yourself too, after the talk. So let's see. Caffe has been taught many things, but maybe not exactly what this is. It has a reasonable guess. It's some kind of vessel or pot, or maybe a coffee pot, but still doesn't know exactly what it is. But that's perhaps something that you could collect data for and try yourself. So to jump back in, one moment. There are many things you can do beyond classification. So one is, we just saw object recognition. It's a cat. You could also do scenes, like this is a city. Or to jump ahead a bit, we can do things more in line with graphics. Like you may have seen style transfer, where we can take, say, a photo of a city in Germany and pair it with different paintings to automatically generate these other styles. And then even beyond pairs, we could even just collect whole collections of images. Say a lot of paintings of French landscapes and also just photos of France, and automatically learn to map one from the other without having examples. No one designed like a zebra-like horse to train this pair by pair. They just collected lots of images of zebras and lots of images of horses, and it was able to learn this itself. Or going back to detection, I want to show you some outputs where this is a model published just last year that's also available online. And you can see it's able to detect many, many things. So in this herd of sheep, it's actually outlined every single one with an exact mask, including the people. And it can do this in only 100 milliseconds. And likewise, these kinds of models are used in more driving scenarios, where we have a street scene with many people, signs, cars, motorbikes. It even knows the person is on the motorbike all together. And this is done every day now. This is something that was unthinkable when I began my PhD only 5 years ago. And finally, we might consider not just detecting things, but finding all kinds of pixel-to-pixel problems, like segmentation, where we want to know what things are, but also in geometry, where we want to know the depth of everything, or all the angles of the surfaces, which could be useful in, say, 3D scanning. Or in colorizing antique photos. This is something we can learn to do by taking the problem backward. We can take a color image, map it to grayscale, and then learn our way to map back. Or in video, we might want to know what's called optical flow, or motion. Because if you're dealing with moving objects, you want to know which direction they're going next. But all of these have the structure of being from pixels to pixels, right? An image comes in, an image comes out. I'll talk about this in more detail tomorrow in the more practical, technical talk, pixels in, pixels out, while this is a more high-level overview today. I'm going to just skip to the fact that while I've been talking about GPUs and servers, these frameworks run on many different kinds of hardware, things like Raspberry Pis or cell phones or other smartphones. And there's many tools to do this in not only CUDA hardware, which you may have heard of from NVIDIA, but also OpenCL from, say, AMD. And many companies are using Caffe and further frameworks such as Facebook, Microsoft, Samsung, and others around the world. It's not something that's just done for research. You can actually do practical work with it. And to give some quick examples, at Facebook, originally all uploaded photos ran through Caffe. That's an incredible number, both for Instagram and Facebook itself, to do things like automatic alt text for the blind, or finding interesting photos, and also, of course, filtering out maybe objectionable content. After contributing back to Caffe for many months and even years, Facebook now spearheaded Caffe 2, which is a successor next version, and leads development of it. And it's now deployed in cloud and also mobile in every Facebook app. Likewise, at Pinterest, they want to do visual search, meaning if I have an image, if I highlight one part, I'd like to know what it is, or even also see similar objects. And they can do this in under a second for millions of requests a day, again, by deep learning. And there are many further things, like in personalization, if you want to give someone restaurant suggestions or help them arrange their photos and save time. This is something that can be done by visual deep learning. So why am I talking about this now? Why am I here? Why am I trying to convince you to do it today and not some other time? And it's especially a reasonable question because there's a lot of history here. Some of the earliest academic research was over 50 years ago. Like, what's changed? You know, and you might have seen deep learning more in the news now. Is it something that's just 4 years old, 8 years old, or 50 or more? What's different now are three key things. One is simply data. We can collect more data, especially with labels, meaning the answers we want, than ever before. And paired with that, we have the computational power to actually analyze this data. And in most cases, this means GPUs. And I want to point out that while many people talk about massive data sets in the millions and large data centers like at Google, say, or Facebook, or other large industry companies, you really only need one GPU to do reasonable work. And that's why it's a more do-it-yourself kind of thing. You just have to be maybe clever about what you try first. Finally, there's a lot of technique that's come in. People have figured out new optimization, new variants and old ideas. But especially, there's new tools for doing rapid research and development. And that's where frameworks come in. So I'm going to go right to what the structure of a framework is. And really, there's a front end. So just like in front-end development, it lets you actually have your language for defining your network and what kind of model you'd like to learn. This goes into some internal representation within the framework, which might interact with tools, like for visualization or profiling or debugging. And then finally, this will be dispatched to a backend to actually do the computation, right? So in this way, we separate how we define the network from how we run it, which is very useful, for instance, when you want to develop your network on maybe a GPU or locally, but then deploy it to many other things, like servers in the cloud or mobile phones. You don't have to rewrite your network every time. The framework can handle that for you. And finally, as part of this backend, there are libraries of all these layers, these transformations I talked about, and also their learning steps for what to do with them. So to just give a quick overview of some frameworks, three that were very influential here in chronological order are all open source. We had Torch, which was a collaboration between NYU, IDSIA in Switzerland, and INRIA in France. This was written in Lua, C++. Theano is a framework from University of Montreal, largely in Python, with some C++ and CUDA there to speed it up in places. And then Caffe, which was started at Berkeley, which had a core of pure C++ and CUDA, so it could be very fast, and then only had interfaces in Python and MATLAB, so you could direct it what to do. All of these are open source. They're all good choices, but also they're all largely done. Torch was mostly discontinued with Torch 7. Theano was done in Theano 1.0, and Caffe is likewise in a maintenance mode since it's 1.0. To make a machine learning joke, people ask me, is a certain framework dying or not? I don't think frameworks ever die, they just converge. We've learned almost everything we can from them, but we can still do new and useful work. So moving to current frameworks, probably many of you have heard of these. TensorFlow is one that's purely industrial. It's made by Google and Google alone, although they have some open source involvement. MXNet is actually made by a coalition. That's both the open source Apache framework, but also Amazon and Baidu and universities like CMU. Likewise, PyTorch is a large collaboration made by Facebook and NVIDIA, NRIA, NYU, and the same goes with Caffe 2, which is led by a whole group of companies. And so all of these are more expressive, efficient, and accessible than past frameworks. And looking towards the future, TensorFlow and MXNet are still very much in development, and PyTorch and Caffe 2 are actually being merged together to do both research and production in a single framework more efficiently. And many more could happen, and you might even contribute to them, because these weren't the first frameworks, they won't be the last. There's more by the day. And one thing to keep in mind is I brought up this idea of sharing models and how that's been so useful in making progress. One thing that all of these different frameworks are working on is a common language so they can exchange their models. And this is called ONNX, ONNX, which is the Open Network Exchange format for sharing things. So now I'd like to just give some brief advice on how you can begin to do this yourself. I'm sorry, but could someone tell me what the timing is? Okay, good. Yeah. And so now, in doing it yourself, with here some various models you could try, I want to be very clear about what you need, because you probably read lots of papers or you see lots of things in the news, and sometimes this can give like a skewed perspective, where I want to bring up that I was actually into deep learning when I began, right? Berkeley wasn't a university that historically did this, and the whole field is very young. So everything I've done and my colleagues have done that I've talked about today was done themselves at the beginning, right? So it's not so different to try it yourself now. So obviously you need an idea, but to start, you could just use a reference, right? People publish blog posts, people publish papers. To begin, and especially to learn, I think it's best to reproduce an existing idea. And because we have this culture of sharing our models now, there's actually often code and models for you to do that. You can look online, and throughout this talk, if the slides are shared later, I've given pointers to links to many of them. You need a framework. You could just do it alone. That's what we had to do back in the day. We had to write everything line by line. But it takes too much time, right? And more importantly, even if you have the skill to write your own deep learning software from scratch, that won't let other people use it, right? Because they won't know how to use it. There's a lot of value to having these common tools and some shared community. And that's another reason to pick a framework. It doesn't matter exactly which. I've talked about several today, and there are surely more out there. But just to pick something common so that other people can extend what you do is a point that's just very important. In my own work, I've, of course, been excited about my research, but even more exciting is to wake up one day and hear from someone, oh, I've taken your framework, I've done this. There's someone in Sweden sorting fish. There's someone in Washington finding invasive plants. There are people helping do medical research faster by analyzing slides. And I wasn't personally involved in any of these, but it's because I packaged up my work in a common framework that they were able to carry it out themselves and extend it. And that's something that you too can be part of. Now, for hardware, you've probably heard of large clusters, or people talk about the latest GPU, but really to get started, you only need one. For many of the projects I showed, like those pixel-to-pixel problems, or object detection, you can reproduce them in less than a day with one GPU. In deep learning, you'll often hear about stories of, oh, this company trained something on 10 million images for weeks or months. You don't have to do that to do useful work. And especially with these kinds of shared models I was talking about, you can take them and extend them in even less time. So this is something that if you can find one GPU, which I admit might be an obstacle, you can do. But it's still at least possible, either by making a machine yourself or finding something in the cloud. And that's very different than the impression you might get, seeing these high-profile stories. And finally, you do need data, but as I was hinting at, you don't need a massive data set that takes years or a huge budget to collect. with things like transfer learning, this idea that you take a pre-trained model, a shared model, and then adapt it to your own task. You can even begin to do work with maybe even just hundreds of examples. But of course, the more you have, the better. And that's another bonus of using this kind of approach is if you design everything, if you have new data or a new task, you may have to start over again if you then want to do something new, right? If I'm trying to make an autonomous car that brakes, maybe I know to recognize bicycles, but it doesn't know about strollers. In the past, you'd have to kind of start over and make a model for both. Now, you can take the model for bikes and then extend it and keep training it and literally make it grow to do new things. And you can do that step by step. So to get into the minimal requirements in a little more detail, again, for an idea, what you should look for these days, which you're lucky to have since it's a more popular area, is you can find a paper with a reference implementation, meaning they have the code online, open source. And the reason to do this is not to just copy what they did and run it, but it's just that you can check your work. When I began, I had to spend even a month plus just trying to get to the same step as an existing paper, just to get to where we already are. But now, you can start at the last step of a paper or project, and you can do it because these things are online. And you can look at some of the pointers that are in this talk for things like style transfer, if you want to try that. And for frameworks, just from my random scattering of meeting people at academic conferences and in my own consulting and industrial conferences, the two that seem to be the most popular and that people have done the most in recent history are both PyTorch and TensorFlow. So I'd recommend these to you. Although the choice of framework is really a personal one and more about style than anything now, because they're all capable of a lot. So you can try it for yourself. And talking about one GPU, originally I actually just had to sit down and build a desktop myself, put a GPU in it, install Linux and everything, and set it up myself. Because there was no other way to run it. That's just what I had to do my research. You can still do that, and it's actually one of the most cost-effective ways to do it. Obviously, you need the parts, but once you have it and power, that's it. A bit more convenient, but actually more expensive, is to use cloud instances. Things like AWS or Google Cloud or Lambda is a new company just doing a deep learning cloud. This can get you started, and it might sound pretty attractive at the beginning with things like prices of $1 or maybe more per hour. But if you consider how much there is out there to do, that actually grows to be quite expensive, especially if these experiments are a day. Like $1 an hour times a few days starts to add up. And as I hinted at before, with data, you don't have to start with all the data in the world. These models actually learn progressively, meaning that if you only have 10 examples, you can train on those first. Then if you collect 100, you can further train it. 1,000, you can do more. And so that's also quite useful if you're trying to get started in this, because you can actually begin immediately. Even though the model, to be very honest, might not be good at 10 points, right? You might need to get more, but you can determine that for yourself. So another thing that I want to talk about is there's all kinds of work that can be done in deep learning. It's not just making a new model or a new algorithm all the time. And it can be easier to start by other avenues. So in particular, I'd like to highlight actually creating something, which can take a lot of effort and resources and time, because especially in research, you might not know what you want to do. A lot of experiments you won't continue with later. You'll try them, it's just trial and error, and you'll continue. Whereas to reproduce something that's already been done, like when you know where you want to go, can be very fast. All of the projects I highlighted, some of them took weeks or months in first developing, not just in machine time, computing, but just in people thinking through it. But each of them can be reproduced on even just a single GPU. Some will take shorter time, some will take longer. But in my own paper, for instance, on the pixel-wise problems that I'll talk about tomorrow, you can get to the end of my paper in only an hour of time. Like, I could literally run the experiment while I talk about it tomorrow, and you'd be done. Which to me is actually quite impressive and empowering. Like, you can do these kinds of things. So to reproduce something or extend an existing thing is actually much more efficient and more accessible. It's something that you could try yourself. And to be a little more concrete and give examples, this idea of transfer learning is we can take a pre-trained model, which is visualized on the left as the features from a network that was learned on 1,000 different classes, so things like espresso cup and avocados and cats and whatever. And then what happens when we run many images through it, where the colors are very general classes. So like here you see, for instance, there's some purple. That's actually many of the animals. Even though it was trained on very specific animals, like this is a dachshund dog and not just dog in general, still it's learned a feature space that has structure, where similar things end up close together. Also in bright green here are all the vehicles. Even though it was trained on things like electric scooter or unicycle, these don't have to be grouped together, and yet, because there are similarities in the visual world, they end up clustering together. And that space that it's learned becomes very useful for other problems. While that model on the left was trained on just normal photos, like you take with your phone, people are able to keep training them for images from remote sensing, like from satellites, that might not even be in regular red, green, blue color. They might be in infrared or ultraviolet, and it still helps. In the same vein, for medical imaging, one can take this color model and instead keep training it on things like MRI or CT. And that allows us to deal with cases where there's very little data, because medical scans can be expensive to do, and some diseases can be rare. So we need a way to work with low amounts of data. And finally, we can switch to other formats even, like things like depth, recognizing things by LiDAR instead of by color. And this can be very quick to do. Like, you can take a model that's pre-trained, and if you say you only wanted to tell cats versus dogs, like I knew someone who actually made a sprinkler for their lawn to keep the neighbor's cats away and turn it on whenever a cat appeared there, but would allow their dog to come home. And that can be done in just 10 minutes. So in open source, there's this saying that many eyeballs make all bugs shallow, meaning that if there are enough of us looking at the problem, it will be obvious to someone. And the same kind of wisdom holds in open science. There's actually a very real need to analyze and further understand even models that already exist. It's not always just making something new every day. We can further our understanding. And this is an opportunity to get involved in the community as well, because while making these models might take a lot of resources and time and in hardware and whatnot, if you have a model that's already trained, it's really just all up to your own cleverness in terms of what are interesting experiments to do to further test exactly what these models are doing. And to be very honest, for many of these models, we don't know exactly what they're doing yet. We know how every individual piece works. We know how we can design them and how we can train them and do new tasks, but there's still some pretty fundamental mysteries to exactly what it is they do learn, in part because these models are so large. They have many, many parameters. There's not simply a dial you can turn and say, oh, make it more like a cat or less like a cat. There's over 100 million settings to the model, which is why we're learning them in the first place. But so to help better understand these things is something that really only more people can solve. It's not something that the research community in its current size can do. And I've seen this already in examples throughout my PhD of people who were new to the field still having very interesting insights and observations saying, oh, did you know if you change the input like this, the model actually is very confused. That was discovered by people who had only been in the field for a very little bit of time. So you too could make these kinds of discoveries. So finally, I'd like to actually just make a note about community and how there is a place for you in machine learning, and then switch to questions, because I feel like a lot of my perspective is maybe more useful to you and your own individual levels of experience. And so what I'd like to close with is that deep learning really is a community in my experience. And a lot of this progress has come from working together on these things. And the form of community isn't this large, hierarchical, world-coordinated effort. It's not this like military fleet of ships where everyone does exactly what was planned. It's this very natural, bottom-up kind of community where people have all sorts of ideas, and small groups actually do much of the work. Even though there are some large universities now and some large companies, every individual project is still usually done by a number of people you can count on one hand. And there's many more people than that in this audience. So you can think about what you can do. So to me, it's much more like a flock of birds, like all the many birds I've seen flying around Yerevan in the evening. So I invite you to join in and find your niche in this ecosystem. This field is getting bigger every day, and it needs more people to help solve new problems. So I'd like to just make some acknowledgements to those who have helped create Caffe and also power much of this research in Berkeley AI research. And thank NVIDIA for donating much hardware, GitHub, of course, for hosting our code and helping us arrange some tutorials, and our many open source contributors in the community. And finally, just thank the whole Caffe crew. This isn't something I've done myself, not at all. The original creator is Yanqing Jia. There were many core collaborators at Berkeley. And finally, I of course have to thank our hundreds of contributors online who have either contributed to the code or helped discuss things in mailing lists or used Caffe in their own work to make new products and new papers. Thank you.
For questions, you can come up to the side parts, and if you want to ask in Armenian, I will translate.
Okay.
Okay, we have one. But please stack up.
And maybe just one note is, although I talked about vision today, if you have questions about other areas of AI and deep learning, I have some experience in that, or I might be able to still speak to it. So feel free to really ask about anything you've seen or anything you've tried.
Hello. Thank you. First of all, thank you for a nice presentation and overviewing the field of deep learning. My name is Alex Sargsyan. I'm from company ENG. I'm founder of ENG, and we are doing deep learning there. I just wanted to ask you your vision about deep learning. Like, it is rapidly developing, and each year on the conferences, lots of new types of layers are proposed, and it is difficult to follow them and reproduce in the production. Just wanted to ask, like, whether deep learning theory will converge sometime and have some concise theory, like similar to the linear algebra or something like that. Thank you.
Thanks, great question. So the question is asking kind of a few things. One is just that there's so much happening in deep learning. How can we track it? And could it maybe be simplified by having one single theory? Because I talked about how there's still mysteries and things. So on one hand, part of all these complications being difficult is really only if you don't already have code for them or examples. So part of this attitude of open sourcing everything, I think helps address keeping up with like the latest frontier, although there's still very many new innovations, so that can't be a full answer. In theory, like in frameworks actually, I think we're more at a step of branching, where people are making more frameworks and more theories before they can actually make the one true one, right? So I think that's a hope shared by many people, but in my experience, there isn't one true theory yet, right? There's a lot of conflicting math, and in part of it is that it's just a very hard problem, right? Like, these networks are much larger than models that we do have good theory for. Like, say, like logistic regression is simpler, so we can say stronger things about it. So for now, I wouldn't wait and hope that there's going to be a theory soon. You should try to keep following everything. But what's encouraging to me is that in these frameworks, they're still finding common ground. Like I mentioned this format, Onyx, which is a way that, say, you can make a model in TensorFlow, but then switch it to PyTorch. Or make something in PyTorch and then deploy it in Caffe 2 because it's faster. So while there's still a lot of diversity there, I think that diversity is actually useful because, again, like I said, it's a very large community and we're still figuring out the right thing to do. I think in both the framework side and development and like the theory side and research, it's more that we have more effort to do in consolidating things and finding the shared parts. That's a pretty broad answer. If you wanted something more specific in theory,
just your idea whether it will converge sometime or not.
Yeah, so I think it will eventually converge, right? Because there are two sides to it. There's the theoretical side, but there's also the empirical side. In computer science, we've often been very lucky to have math and logic and things where once you prove it, it's true, right? Like theorems are just very deeply true. But the rest of the sciences, like biology and physics, have to be empirical. They have to do experiments. Deep learning is in more this empirical phase. And that's all right. If we still are very rigorous and design the right experiments and are careful about what we change and what we predict, then we can still learn from this. So I think in some sense, like empiricism is the true theory of deep learning. because everything else is, conjecture, because we can't yet verify it. But I think there will be a theory. My personal favorite are the more information theoretic theories. So if you look at, for instance, Stefano Sawato is a professor at UCLA. If you're interested in theory, I'd really recommend you look at some of their papers.
Thank you very much.
Thank you. I see a speaker has a question.
Yes,
Perfect.
Yeah, hi Evan. I'm Daniel. I have my presentation right after Evan, and I'll speak about electric transportation and transportation of the future. So Evan, I have really question in your area. So what do you think? In how many years the artificial intelligence transportation will replace the human-driven transportation? And what is the biggest challenge in it?
Sure. Okay, yeah, so this is a very hot topic. People are discussing this all around the world. So to me, I think the key thing to keep in mind is that humans actually aren't perfect drivers. We make mistakes all the time, right? And we have to do so many things. Like, you're usually not just driving, maybe you're thinking about who you're going to meet, or you're tired from working all day. At least one advantage of machines is that if we can figure out the right thing to do, they can do it constantly and tirelessly. Actually, some of my own research is used in prototypes for autonomous driving. And if you get in these cars, and they have like a debugging output where you can see everything that it sees and what it's inferred it to be, you can tell almost immediately that it sees in a very different way than people. For instance, it doesn't have attention. It doesn't look in places sequentially. It can look everywhere at once. But I'd caution you that that doesn't mean that we're done. Because one thing that people still have that's a supreme advantage over all of the machine learning systems is that people can think about how much they should think about the problem. You can recognize if there's a confusing situation on the street, like construction, or maybe someone's lost and going the wrong way up a street. In all our current machine learning and vision models for autonomous driving, they can only do a fixed amount. So they'll look everywhere in the scene and stare, but they'll only do that for their 10 steps, and then time is up. And we don't know how to design and learn, at least yet, systems that are able to take more time and elaborate on what they're going through, what they're processing. So I think for more limited scenarios, things like doing shipping on highways, that will be, I think, more common, at least in the US, maybe also in Europe, within 5 years. Tests of it, because it's a more simple setting, if you think about it, right? Like, highways are pretty controlled and maintained. But for things like city driving, I can't even begin to guess when it will actually replace people. And even the highway estimate is only an estimate, right? Like, obviously things can change. Because while there are very exciting examples and people enjoy even having these early self-driving cars with things like lane following, a lot of them actually rely on there being human drivers on the road. Because a lot of what they learn is to follow what the other cars are doing. So if all the cars were autonomous, they would just follow each other into a wall. That's an exaggeration. Obviously, people are working on it harder than that, and there are improvements. But sometimes if you see an exciting demo, that doesn't mean it's ready. And another part of it that I think is very interesting, and it's work done at Berkeley, is you have to consider not only the car, but also the infrastructure. Right? If more of the streets, like streetlights, could actually communicate with cars and say, oh, there's been this much traffic today, they might be able to decide different routes. And so people are actually coming at it from the infrastructural side and the vehicle side at the same time.
Thank you very much.
Sure.
Hello, my name is Arsene. I have the following question. I was one of those who thought that, as you referred to in your speech, that Caffe framework is dying out. And I was surprised to hear that Facebook is using Caffe 2 in production for some visual tasks. So can you elaborate more on what Caffe framework has, what advantages Caffe framework has over other frameworks like TensorFlow and PyTorch, and why Facebook is using Caffe 2 in production over other frameworks?
Sure. So to speak specifically about Facebook, they actually not only run Caffe 2 now, but they ran Caffe before that. So some people associate Facebook with Torch, because that's a framework they used for some of their research, but actually it was never in production. Facebook adopted Caffe as it came out of Berkeley and had an engineering team who used it, mostly because Caffe is a very lean framework in a sense. And in part, that was because of necessity. It was made by only a handful of people. So it had to be simple and kind of small enough so that that many people could actually develop it and maintain it. And that also lets companies like Facebook, but also Samsung and Sony and others who've put it in production to modify it themselves, right? Like TensorFlow does many things, but it does many things in many ways with a lot of code. So it's hard to kind of tune it yourself if there's one specific thing you want to do. And having a linear framework can be good for that. So that's specifically about Caffe. I want to give a more broad answer, just kind of generationally. Frameworks change over time, right? Part of the reason we have Caffe is the other tools weren't fast enough and weren't flexible enough. They couldn't do things like branching architectures and various things, so we had to write it. But now it's 2018, right? If you're all starting, you have the choice of frameworks today. So for that, I would actually recommend things more like PyTorch and Caffe 2 and like TensorFlow than beginning with Caffe itself. I think there's still lots of reference implementations and projects in Caffe that can be learned from. And the same goes for Theano and Torch, even though these are also somewhat done in a sense, or as I call them, converged. There's still lots of ideas there, and there's lots of techniques that because of these core ideas being shared, really all these frameworks are trying to do the same thing, you can still use those in a new framework. Were you also asking about, among new frameworks, why does Facebook use PyTorch and Caffe 2?
No. So Caffe 2,
Yeah.
Facebook still uses in production Caffe 2 or not?
Yes, that's right. Yeah.
It does.
So all of production Facebook, so every image you upload to Facebook.com goes through Caffe 2 models. A lot of the text you write for translation goes through Caffe 2 models. When you're on your phone and it finds your face or helps you do a different style, those are Caffe 2 models.
Is it lightweight or what? Or was it historically like they implemented it first but they didn't want to change it?
Oh no, so they're actually implemented in concert. Like Facebook decided to do both PyTorch and Caffe 2. And then Onyx, that exchange format, was a bridge between them that now is more general and can be used by even more frameworks. But the reason for Caffe 2, or kind of a general trade-off in frameworks, is that some can be very expressive, meaning you can write down any kind of model, but often that's a trade-off for efficiency. And really, in research and in industry, it's the product of those two, right? You need to be able to express your model, but also run it. If you can't actually compute it, it's no good to you. So Caffe 2 was designed to be simply faster from the beginning, and also able to target more platforms, because it has its own representation of the network. This is like internal network representation I was talking about, and that can then be shipped to all different platforms. So there's something called Caffe to Go that runs on like iOS and Android, but also Raspberry Pi. I don't even remember all of them, to be honest. It's also like Metal compatible, I think, on Apple platforms. Whereas PyTorch basically runs on Linux and like kind of on Mac. PyTorch basically runs on Linux, like on a GPU, on a server desktop, right? Like it's really not that platform agnostic. And that's fair, because on that platform that it's made for, it can do very many things. And it's almost like writing native Python. You can use all your debugging tools, all these things. So it's very nice. But because of the design choices they made to make that possible, it kind of inherently limits how efficient it can be as well. I hinted at in kind of the future frameworks, there are ways to try to merge these. So at present, there's PyTorch and there's Caffe 2, and Onyx goes between them. But now they're actually merging these interfaces. But because they had that nice separation, they're kind of encapsulated into here's my experimental code and here's my deployment version. There's hope they can actually reconcile the two, so that you kind of can be in experiment mode, and then you have to do that on a given kind of computer with a certain developer setup. But then having done that, you can flip a switch and say, now I want to go into production mode. And if you run things, it will actually compile that into a different format that can then be deployed to all different sorts of things. That's at least the plan.
Thank you.
One last question.
Hello, does it work? My name is Daira. I'm a graduate student from Kent State University, Applied Statistics, and I have a question. We know that Berkeley University and Armenia are worldwide famous as astrophysics centers, science research, and do have some collaboration or application with astronomy. I mean, in finding nebulas or exoplanets. Just I'm interested in application of statistics in such way, and deep learning and machine learning, artificial intelligence in this way?
Yeah, so there certainly are. I could tell you in more detail offline if you come find me. But in a lot of sciences like astronomy, but also biology, where they have slides, and even ecology, where they're studying animals from airplanes or maybe satellite images, there's too much data to look at by hand. That's especially true of space. And so people are using machine learning more and more for these things, both Caffe and other frameworks. So it's a very good application.
Thank you.
Thank you very much. And to remind you, there will be a machine learning panel discussion after the next talk, so you can ask more questions. Thank you very much.
Thank you.